So as was said, what I want to talk about today is a bit about offloading technologies for the theme of this partial section of the workshop, and specifically talk about capabilities that exist in BlueField-3, as well as the data path accelerator. So the first question to ask is why do we care about Accelerator about asynchronous agents? So I view these sort of technologies as asynchronous agents that can be used for potentially accelerating communication, helping overlap computation and communication, as well as allowing some other things, some new algorithms that you can't if you're not working in an asynchronous environment. And so the main goal here at the end of the day is to accelerate applications, right? And it's not to write yet another collective communication algorithm or whatever type of communication algorithm you want to write, or do some of these application offloads that have been talked about in the previous two talks. So really, all these technologies are aimed at reducing time to solution. And so this is really the context of the work that's being done. So if you think about traditional server architectures, um, if you think about traditional server architectures, typically you have the host and the network sort of separated from each other. The network, if you have InfiniBand or something like that, the network maybe do some work that helps the host in terms of communication, but in general, they're really decoupled from each other, and they don't work very well. They're not designed to work cooperatively. But with the introduction of smart NICs or whatever you want to call them, one of the goals is really to change the server architecture and to move capabilities from or to move work from the host, from your computational engines to these asynchronous agents, to let the host really focus on what it's built for, and that's computation, right? Rather than have it do everything. So in this case, in the case of the DPU, I'll also mention the DPA a bit here in a while. The goal is really one of the things that we've offloaded to the DPU is communication management, portions of communication management. It doesn't make sense to move it all wholesale. I won't go into those details much today. You need to be careful in how you do things, like in any computation. You have to be careful in what you have done, what you do. And so that's really the point, or the driver for this work. So I'll give a bit of a description of the DPA, the DPU. I'm sorry, NVIDIA's Bluefield DPU. There's been some description of it before. Uh, so the Bluefield DPU is a system on a chip. So it contains, I'm not sure where it appears here on the figure. It contains the ConnectX core, full ConnectX core, and it also includes a set of ARM processors. They're processors that run independent of the host. They're normal ARM processors. Uh, they have their own memory subsystem. They run their own OS. They can take user provided code compiled with your standard compilers and the like. So it's really in a lot of ways it's a just another server attached to the GPU, to the ConnectX core. There still is a PCI bus separating them, so you don't benefit from being really closer to the network there. There are some benefits for some situations, but that's not the main design point there. Bluefield 2 and Bluefield 3 are the devices that are most well known. We're on Bluefield 3 now. I have a bit of statistics here in terms of performance capabilities. So the Bluefield 3 device is the NDR, or 400 gigabit per second device, has a message rate of 370 million messages per second. So it can drive a lot of data into the network. So it's that message rate is strictly the message rate of the core. It has up to 16 ARM cores in it. I forget what version they are. I think it's A78. It has reasonable compute capability. It's not a strong server by any means. That's not its intent. It has, if you're really looking for a lot of computation, this is not the device to buy. Right? Buy a regular server. This is intended to supplement, to help specialize specialize and help increase system efficiency. Memory bandwidth in BlueField-3 is substantially larger than that in BlueField uh, um, 2, and the key point there is it's higher than the network bandwidth. So it has a chance, if you're not going to do anything with the data, if you're not going to manipulate the data, to actually saturate the wire, whereas BlueField 2 didn't. Uh, so those are from a communication library perspective, those are the key characteristics of the device. There's one more thing that really helps in terms of being able to effectively use the BlueField in the context of an application, not just in the context of a benchmark. And so what happens here, there are these there so um, when you move data around, somehow you have to the network device has to know how to access that data. And in the land of InfiniBand, Rocky, and the like, in NVIDIA devices, um, memory keys are what are used to identify that memory, and memory keys are things that hardware understand and know what to do with it. So there's a very special memory key that you can set up for memory that you can set up for memory that can be accessible, so that host memory can be accessible by the DPU. Right. So there's some extra work that you need to do when you set up these memory keys. Uh, to be able to have the DPU basically move memory on behalf of the host, right? So you don't have to copy memory to the memory of the DPU to be able to send it. You have to set up a special memory key, and that's all. And that's really a very important feature when you're trying to move data around, and it's something that helps you have a chance of getting some good performance with these devices. Um, NVIDIA also has a second asynchronous agent. This one is actually resident as part of the ConnectX core. And it's called the Data Path Accelerator. The Data Path Accelerator includes in current technology includes 16 RISC-V cores that are part of the ConnectX core. So you have those in ConnectX 7, ConnectX 8. These they support integer arithmetic. They don't support any floating point arithmetic. They have their own caches. They can also access host memory. Each of the 16 cores can drive as many as 16 um, threads, and so you can use, and they're also user programmable. So what you can do is you can use those processors to also drive data and not data, also drive the network. You probably don't, if you can avoid it, you probably don't want to move memory into the DPA to send it out. That's probably a bad idea. But a key difference between the DPA and the DPU is that since the DPA is part of the ConnectX core, it has very fast access to set up communications, right? Again, it will move data on behalf of data that's host resident. It doesn't have to be, and you don't want it to be in the DPA. So this is very good for orchestration. So if you need to coordinate with traffic, if you need to do, we use it for some of our congestion control, for example, stuff like that. This is a very good device for that sort of work. I guess we have here the statistics, and I won't, if you can see them in the slides later on, the amount of memory that exists and caches and the like. And again, as I mentioned, you can access quite a very large memory footprint on the host. Right. From a use perspective, there are just a few things that are important to recognize when you try and design an algorithm for this. So first of all, the threads that run on the DPA are short-lived. If you don't terminate the thread on your own, the OS on the DPA will terminate it for you after it's been running for a few seconds. So it really lends itself very well for event-driven type of operations. So if you think of your communication libraries, you probably don't want something polling there to find out if you have work. Because if you do, after a few seconds, it's gone. So you have to have a mechanism for restarting it. And most communication libraries are not set up for that sort of stuff. And you don't want to set them for that sort of stuff. Memory is persistent. So that is the persistent foothold you have on an environment. Even if a thread goes away, your memory remains. And so that's what gives you a long-term context that you can use for things like communication optimization. And those are probably the key things right now. So we're in the process of trying to understand ourselves how to use this in a good way. There's support for this. There's this library called Doka, in this particular case, Doka DPA, that supports programming here. And there will be a talk about Doka, another thread on Doka UROM will be given later today as part of this workshop. So a few things that need to be taken into account when you design offloading, trying to offload work to the DPU. When you're trying to do stuff that traditionally has been done on the host, but now you want to be able to have predictable progress and do this using the asynchronous agent. So the obvious thing is there has to be some mode of communication between some mode of coordination between the host and the DPU, or your asynchronous agent. And one of the things I'm alluding here to is probably the best solution is not to take what you do on the host and move it wholesale to the DPA. You probably won't get the performance you want most of the time. You'll probably harm your performance. And so it's really important to think about how to do this correctly. Again, typically these offload engines, so these slides are focused on the DPU, but it's the same idea for the DPA and typically for other smart NICs, is the computational capabilities are usually less not as strong on the DPU as you're strong or on your server processes. And so you need to take that into account when you decide how much work to put there, right? So if you try to do things like packing data or other things like that, you need to think hard if you want to do that or not. Yeah, I think these points probably aren't so relevant. In terms of network access, I mentioned already the ability to address or to process data that's host resident. That means if you have your application data sitting there, the application data can be moved by whatever communication library you use without actually moving the data to that asynchronous agent, which is what you want. The device is also agnostic of network devices are agnostic of what type of memory sits on top of it. They don't care if it's GPU, CPU, whatever. It can do work on behalf of them because it just doesn't care. Let's see the stuff that's relevant here. And another important thing to remember here when you design things is you don't have to be able to do your management work as fast as you can on a standalone strong processor. You have to do it just fast enough so that you keep the network busy, right? So that's all that really matters here. So from a processor, from a software component portion of things, the work that we've done in the past is focused really on collective operations. We're doing some other things right now with distributed tag matching, but we have all the collective work is done in the context of UCC, of the UCC communication library. So for those of you that are familiar with UCX, it's from the same family of libraries. We create, and for the DPU, we create long-term processes called service processes that live on the DPU. They belong to the application, and they're the ones that do the work for to the communication work, the orchestration work. And a single service process will serve multiple host side processes. So if you, in the context of MPI, you might have one service process processing work on behalf of, say, 10, whatever MPI processes. So that gives you that actually that's required because of the amount of resources that you typically have. You don't have a one-to-one mapping between CPU cores, for example, and DPU cores. So you need to do this thing, but it also gives you opportunities for optimization. We created a runtime. I'm not going to talk about it, Mimosa, to help these sort of things. It's sort of a precursor or whatever you want to call it to Doka that will be talked about this afternoon. And for moving data, we use the UCX interface. But an important thing, probably the most important thing here is because these devices are asynchronous, it gave us an opportunity to rethink how implement algorithms for collective operations. And specifically, we focused on ones that move very large amounts of data. So you think of your all-to-all V, and the like. The data for the algorithm that is used to drive the data. You know, if you think of your ring algorithm and the like, that's driven from from the asynchronous agent. So it gives us opportunity to deal with load imbalance in the application, which you cannot do if you're running your MPI library on the host, because it's sharing time with the application computing. A cartoon here of just describing what I talked about in words, where the extension, where UCC is basically extended. There's coordination between the host and the DPU in the context of a single MPI process in this case. Picture a cartoon here of the MPI tasks and how they map to the service processes on the in this case the DPU and the various communication paths that exist for the work. Very quickly, I'll talk about performance evaluations here. So we implemented, if I remember correctly, about four different algorithms for the DPU, all-to-all V, all gather, and all gather V, and algorithms, short, long messages, or at least partial, and this here basically gives this slide here shows the latency as a factor of the number of progress threads we had running on the DPU. I'm sorry, let me say that again. The number of MPI processes that one of those service processes runs on the DPU, anywhere from a 1-to-1 mapping up to an 8-to-1 mapping. And the key takeaway here is once you've gotten up to two actually your best performance is when you have only a single service process. In this case, it's four service processes that are four host processes that are managed by a single process, but you maximize at about a 1-to-8 ratio. That is one service process for 8 MPI processes. You've already gotten most of the gains you've lost most of you get most of your loss at that stage. So you can really have a many-to-one type of optimization or management that works well. In this case, the latencies here for the all gather and the non-blocking all gather. Uh, uh, we have a comparison here of the performance, absolute performance. This is in the context of an OSU benchmark, so it's a primitive benchmark. It's the best thing that you can get. It doesn't reflect what happens in applications, but this is the first way people measure algorithms. And what we can see here, generally, the green boxes are the green lines that correspond to the offloaded using the DPU offload algorithms. We compare it with HPCX, two flavors of HPCX, two data layouts, process layouts for it with HPCX and with OpenMPI. And so in general here, what you can see looking at this is the offloaded version works well. Its latency is comparable to a correctly laid out MPI process on your process grid, on your host process grid. The reason we don't take the performance penalty that OpenMPI does if you go from a contiguous distribution of data to a stratted distribution, because we look for those sort of things in the optimization. We don't fall into the trap, and OpenMPI in that case didn't. Or HPCX, I should say, in that case did that. OpenMPI it doesn't perform as well. So the point here is the performance is good. You get the performance, very good performance on primitive benchmarks. You get very good overlap, as you would expect, because this is what the hardware is designed to do for over the full range of messages. So you're able to really have traffic progress independently as communication is going on the host. But when it comes to applications, this is where you start to see the benefits of the new algorithm, actually. And again, the emphasis here is without this asynchronous agent, you could implement the new algorithm, but it would be useless because it doesn't have the necessary information to deal with the load imbalance in the application. So we ran an FFT algorithm that transformed four variables in parallel, and compared it using a variety of different communication libraries, OpenMPI, both blocking and non-blocking, as well as yeah. And we also measured it against ran the collective blocking and non-blocking from the DPA. And in red, we have the performance improvement for over a range of process distributions. So, and so we can see that with this the offloaded algorithm, the non-blocking algorithm outperforms everything else in terms of the FFT, anywhere from as little as what is it, 10% to as much as almost 50%, depending on the particular parameters used for that FFT. Don't have time, so I won't go into the details. We also ran a materials science application from Max Planck Institute. It's called Octopus. It's used to do some, I think they do DFT calculations here. We compared total runtime using HPCX, which is NVIDIA's optimized version of OpenMPI, vanilla OpenMPI, and then the offloaded version of the library. And we got as much as, if I remember correctly, it was, I think, 15% improvement. No, actually, no, I'm sorry, it was 20-some percent improvement in overall application runtime. And again, that application happens to have a lot of load imbalance. And these asynchronous agents give us a way to deal with it. And so, problems that exist with, standard implementations, we just work around. So again, the slide I started with, this is data for four applications we worked on. These were selected just because we needed them for RFP responses. Green is higher is worse. Green is the standard MPI, not offloaded MPI, and blue is the offloaded version of using the offloaded version of the. In this case, it was an all gather V. So we can see the benefits, general benefits for applications. That's it.
Right. Get time for some questions. Yes. Okay, that was a cool talk. Thank you. So I'm late to the party on BF-3. We've got them in the data center. We've had them there for a while, doing various things with connected to accelerators and big systems. But a lot was made a while ago about the use of BF-3 to accelerate file system I/O. People talked about putting Lustre and, as a POSIX client and GPFS and an MSD onto the BlueField chip, and using it as a means to aggregate away CPU cycles that would be otherwise more useful on the node for actual computational platform, rather than burning it that way. You could put it onto the BlueField. That sort of died off, and I haven't heard a lot about that. And some of what you just said there sort of suggests and sort of warns that it might not be the best use, because you've skewed the talk towards talking more about MPI and collectives and doing things in an optimized way. So can you speak to whether people are still doing that kind of work with file systems?
Yeah, so first I'll say I'm not in my group. Actually, we do have one person that's very strong in file systems, but we don't do file system work. So that's why my talk wasn't about file systems. As far as I understand, there is work continued for that. BlueField is specifically targeting those sort of workflows. Yeah, and moving forward, so BlueField has moved from targeting the whole world to really targeting north-south type of traffic. So definitely storage and stuff like that. Yeah.
Thank you. Any other question?
So when you're developing these applications, how replicable are they kind of to other platforms? If you're trying to use other accelerators, or maybe switching it to systems that don't have accelerators.
So what this needs is algorithmically, all it needs is an asynchronous agent. Nothing in the algorithm is specific to BlueField.
Okay.
BlueField, it gives you some advantages that, again, if others I can move data with BlueField, not have it's not sitting in my DRAM. I can move it, but there's nothing in the algorithm that's BlueField specific.
Okay, great, thanks.
Yeah.
We have more questions. I have a final one. So in your graph that you showed, it was always like vanilla OpenMPI, and it was the HPCX version of OpenMPI from NVIDIA, and then there was this offloaded version as shown here. And I was wondering, like, is it available to us as users, this offloaded version? Should I just use UCC, or what should I do?
No, so NVIDIA is targeting BlueFields now for north-south traffic, not for east-west traffic. And so this is a nice research project, showed a lot of benefit. If it showed the benefit a year earlier, maybe the picture would be different, but no, there's not. But the algorithms themselves, we're actually moving to other contexts. As long as you have an asynchronous agent, so that's what we're doing with the DPA. That's what we're doing with our GPUs. So the algorithms themselves, even though they aren't making themselves out into the product with DPUs, they are making themselves out to the product with other hardware that exists. Okay. And they will be available in those libraries, the library you mentioned, as well as others.
Yeah, the benefit from that. Yeah. Okay. Thank you very much.